So what I'm going to do is I'm going to go through these next 3 rules, and it's actually going to help us to go over electron configuration and then introduce a new concept, which is the orbital diagram. So the first principle you've actually been using without realizing it, or maybe you have realized it, but the Aufbau Principle states that each electron occupies the lowest energy orbital available. Now, you've been doing this without even realizing it. Since you've been using the periodic table, starting with 1s, so like for example 1s2, 2s2, 1s is lower in energy than the 2s. So you first fill the 1s orbital with 2 electrons, then the 2s with 2 electrons, then you get to 2p, that's the next highest, and then you fill it up to, let's say, 6, all right, and you keep going. The 1s is lowest in energy. However far you go, that'll be the highest in energy. So you're already following his rule, which is saying you first occupy the lowest energy orbital. Awesome. The next principle is Pauli exclusion principle. And that states that a maximum of 2 electrons, so 2 electrons, are allowed in a single orbital. Now remember, for the s orbital, you only have that spherical shape. So that is one orbital, that's one shape, one version of it. All right. For the p, you've got 3 different orbitals. You've got the p along the x-axis, the p along the y-axis, the p along the z-axis. So you've got a total of 3 orbitals for p. So I'm going to write that here. So s, you only have 1 orbital. P, you have 3. For d, if you look, you actually have 5 different shape options, different volumes that the electrons can occupy. And f, if you see a pattern, 7, 1, 3, 5, and 7. Now, I'm going to show you how to write this. So, I'm going to write out the orbital diagram of beryllium, keeping in mind that only 2 electrons can fit in each orbital. And those 2 electrons must have opposite spins. So, I'll show you how this works. Don't get overwhelmed. All right, for beryllium, my electron configuration is 1s2 and then 2s2. That's it. Okay. So remember, for s, you only have 1 orbital, so you're going to draw 1 box, because we're going to represent each orbital with a box, because that's easier to do. And I've got 2 electrons in here. So I'm going to show 1 with a spin upwards and 1 with a spin downwards. They have opposite spins. That's 2 electrons. Each half arrow, or you can do a full arrow if you want to, it doesn't matter, represents 1 electron. So 1, 2. Now for 2s, again, you only have 1 orbital. And again, you've got 1, 2 electrons. All right, so not too bad. Beryllium's pretty nice and easy. Let's go on to Hund's rule, and then we'll get a little bit of practice. All right, Hund's rule states that single electrons with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the same orbital. Oh my goodness. Okay, we're going to go through oxygen as an example, and you'll see that this is, even though the wording may seem overwhelming, it's actually quite simple, and it actually makes sense. It helps you to fill the orbitals. So for oxygen, my electron configuration is 1s2, 2s2, 2p4. All right. Remember, for s, I have just 1 orbital. For 2s, again, I only have 1 orbital. For p now, all of a sudden, I have 3. All right, so there are 3 orbitals right there. Awesome. And now I'm going to fill them. So remember, according to Pauli exclusion, my electrons have to have opposite spins, and there can only be 2 in each orbital. So for the 1s, I've got 1 here and 1 there. For 2s, 1 there and a second 1 there. Now here's where Hund's rule comes in. I need to fit 4 electrons, and only 4, in this 2p orbital, in these 2p orbitals, 1, 2, 3. All right. I've got to place my electrons one at a time so that they have the exact same spin, and then what I'm going to do is I'm going to go back, and any extras I'm going to put them in with opposite spins. So I'll show you. I need a total of 4 electrons. So I've got 1, 2, 3, and then my 4th one's going to have an opposite spin, so 4. All right. Now, I'm going to do chlorine with you to show you how to do it, just to make sure we're on the same page. All right. So For chlorine, I'm going to first write my electron configuration. So I've got 1s2, 2s2, 2p6, 3s2, and then it's 3p5. Alright, so I'm now going to draw my orbital. So for 1s, remember s only has one orbital, just the sphere. 2s, again, just the sphere, one orbital, but it's just bigger. For 2p, I've got 3 orbitals. And if you guys see, I'm lining them up with my electron configuration just to help myself out and to help me as a grader out as well. For 3s, remember again, s only has one orbital. And for p, again, 3 orbitals. 1, 2, 3. All right, now I'm going to fill it. So, electrons. Let's do this. I've got 2 electrons here, so one's going to be spinning up, one's going to be spinning down. For 2s, I've got 2 electrons, one spinning up, one spinning down. For 2p6, I've got to fill it according to Hund's rule. So I'm going to have them all with the same spin, and then I'm going to go back and fill. So I've got 1, 2, 3, and I'm going to go back, 4, 5, 6. Okay, that works out perfectly. For 3s, I've got 2 electrons, so one up, one down. For 3p5, I've got 1, 2, 3. Then I'm going to go back, 4, 5. So notice, if I were to ask a question like, I don't know, how many unshared pairs of electrons does chlorine have? All of these guys are shared. They have 2 electrons, the pair, except for this awkward guy at the end. And so in a question where I say, how many unshared pairs of electrons does chlorine have? Your answer would be 1. All right?